The broadcast is now starting. All attendees are in listen-only mode.
And good afternoon and good morning to everyone. This is the Nautel webinar on asymmetrical sidebands and HD PowerBoost, coming to you from lovely Halifax, Nova Scotia, right on the side of St. Margaret's Bay, where it's probably a good bit warmer than it is for most of the United States at the moment. It was 50 degrees at parts of last night. And that is not to say that winter weather is not coming down the road. If I can make this thing advanced slides. Okay. So I'm Chuck Kelly, the Director of Sales of Nautel, and sitting next to me is Mr. Philip Schmidt, Research Engineer for Nautel. Good morning, Philip.
Hello.
And we have Mr. Jeff Welton, Regional Sales Manager for Nautel. Come on, scoot in here, Jeff.
Good morning, everybody.
All right. So we've got just a quick webinar, but I think it's going to be a very interesting one today to talk about the digitalization of HD radio and the power increase, asymmetrical sidebands, HD PowerBoost, these subjects, and what they mean to you. And we're going to give you an opportunity, you notice I've got it in red here, to have a live demonstration. We've got some kind of exciting things to share with you today, and we hope to make this a well-spent 30 or 45 minutes. So just a little bit about Nautel. As I mentioned, we're on the shores of St. Margaret's Bay here in Nova Scotia with offices throughout the United States as well. This is actually our 41st year, and we started making solid-state transmitters in around 1972. Radio transmitters, and Nautel, interestingly enough, a little fact that some people don't know yet, and that is Nautel has never made a tube-type transmitter. So we've always been on the cutting edge of solid-state radio transmission. I guess the first question people have to ask themselves is, why are we talking about an HD radio power increase in the first place? And Philip, I think that a lot of it has to do with improving building penetration.
Absolutely. Even with some of our own testing, once you start walking into supermarkets and whatnot, you very quickly lose reception of handheld devices. Certainly more power helps.
And improving the outdoor coverage to 60 dBu contour and beyond, less blending, multicast dropouts, better reception on portals. But a lot of it really boils down to, at the end of the day, an argument having to do with noise floor. Let's talk about how this can be implemented. The bottom line is increasing the digital subcarriers from the -20 at the introduction of HD PowerBoost, or HD radio rather, to -14, which is approved for stations across the United States. But even beyond that, in special situations where the additional coverage is needed, and the proper authority can be gotten from the FCC. The easiest way that people are looking to do this is to simply improve the power level of a solid state or tube type higher power transmitter operating in the hybrid mode, where both the digital and the analog signals are being amplified by a common amplifier. And hybrid mode might also be known as a low-level injection in some cases. Now, with the higher HD injection level, that can reduce the analog TPO capability. And that's because the peaks are higher for the digital signal, and they have to be accommodated by the peak power capability of the transmitter. But it also means that the analog transmitter has to go down to a lower average TPO capability in order to be able to accommodate that. So in some cases, with customers, it may mean replacing their existing transmitter or combining another for a higher total power. And higher injection levels do potentially reduce the efficiency of the transmitter. On the other hand, as we'll see later in the presentation, HD PowerBoost increases the digital injection and the efficiency of an existing transmitter. We'll see a very, very good demonstration of that in a few minutes. So a lot of the reason why HD power levels are being increased is because of noise considerations. Philip, would you like to talk through some of this?
Sure enough. It's certainly no secret that as more and more electronic devices become available, the noise floor in the radio spectrum is increasing, as you can see by this animation here. And certainly, with the initial rollout of HD radio, it was very apparent that a minus 20 dB C injection ratio was not quite enough for building penetration and for coverage. Certainly, as the noise floor increases beyond that, now you can see there's no IBOC left. So certainly, increasing IBOC power, it's a no-brainer. It does make sense to do that, and as also shown in this graph here, even if one of those sidebands is peaking out of the noise floor, we can certainly get better coverage improvements.
Why asymmetrical?
Why asymmetrical? Well, certainly we need to manage, just increasing power it is a simple solution, but certainly the more power we put on air, the greater chances of interference. So asymmetrical gives us a toolkit to manage interference. We can selectively increase the power in either one of the two sidebands, and by doing so, we can either be a good neighbor to our adjacent stations, or we can get more coverage by going up in one of the sidebands.
Let's look at this another way. If a station has a first adjacent station that is close by, they may not be able to increase their signal all the way to minus 10, but they may be able to increase the other sideband. They may not have that competitive situation on the other sideband. So what asymmetricality allows is increasing the injection level of one of the sets of sidebands, say the lower sideband, while leaving the higher sideband limited so as to protect and free from interference the upper first adjacent channel. Okay, and as we're going to show here in a second, up to 4,000 stations in the United States can benefit from this. There's been some studies done. National Public Radio did an excellent study that showed up to 4,000 stations may be able to take advantage of asymmetricality to increase their coverage. And this technology, although all we're talking about today is FM, this technology also works on AM. Funny how about physics that way. But there are stations, I believe, that are on the West Coast that are doing asymmetric on AM so as to allow them to continue to have the coverage area they need while protecting a first adjacent channel on AM. So this shows a basic graph. And this is basically some of the FCC's criteria. This shows the proponent station is your station, and the protected station is your first adjacent station. And it shows that if you can always go to minus 14 if you can be below the contour on the adjacent channel of the 57 dBu contour, then you can go to minus 12. And if you can stay below the minus 60 dBu contour, it means you can go to all the way to minus 10 potentially. And this is part of the NPR graph, our chart, which shows that up to 5,000 stations can take advantage, or 4,000 stations rather, can take advantage of asymmetric power and improve their coverage while still maintaining protection for adjacent channel stations. Philip, you're going to have to walk me through this one.
Yeah, sure enough. Well, one of the questions that I've had repeatedly from broadcasters is, assuming that, yes, we understand the benefits of asymmetrical sidebands and all that, given that I only have a certain amount of digital power, am I better off moving all my digital power on one sideband, or should we balance it? So what we're looking at here is a bit error plot that we've used to see what the digital coverage is, both with symmetric and asymmetric sidebands. So there's two lines on here that you see, that one that's kind of orange and one that is green. Those are the symmetrical curves, both for minus 10 and for minus 14. And we're comparing here also PowerBoost versus standard IBOC. Wanted to make sure we've got the same performance here. But the interesting thing is the blue line, exactly, the asymmetric line, where one of the sidebands is at minus 10 and the other one is at minus 14. Between the two orange lines, there's really nothing interesting here. Increasing power by 4 dB simply means you get 4 dB more coverage. So it's a shift of the curve to the left. But with asymmetric sidebands, what you'll see up towards the IBOC reception limit, you now almost have something equivalent to running, let's say, something just under minus 12 dB. So if you move over here, so you can see the asymmetric sideband gives you a spectral efficiency improvement in essence, or an improvement in coverage almost by almost 2 dB. Now, however, if you had used the same amount of power and moved that across to, let's say, minus 11.5 dB injection ratio, which would be equivalent power of minus 10, minus 14, you would be a little bit better. So the conclusion from that is, as you're considering to move up your power from minus 20 to minus 10, do it symmetrically as far as you can. And only once you can no longer go symmetrically, you will get further improvements by going asymmetric.
Okay, so in other words, the Ubiquity HD system has always been based on the synergy that you get from both sets of sidebands having the same information loaded in it. And this simply shows that. We would expect that an asymmetricality where we have minus 10 and minus 14 would be somewhere between the coverage of a all minus 10 or all minus 14, but it isn't quite as good as 50% the way. Okay, so that's pretty much what we would expect, but it's nice to see it. This shows the general timeline. We've been talking about increases in HD injection level as far back as 2007. There were 9 special temporary authorities issued by the FCC, and there was a number of tests, coverage tests, interference tests, evaluations that were done, and then finally the FCC last fall approved the power increase. WAMU in Washington did a trial, which we'll explain, and the FCC has, in some cases, under special temporary authority, allowed asymmetrical sidebands. And looking ahead to a few months, Nautel will be making the first volume shipments of HD PowerBoost, which includes asymmetrical. So we took, primarily Philip, took asymmetrical sidebands to the NAB, and we were very proud to have won 2 awards, the Cool Stuff Award from Radio World and the Innovation Award from Radio Inc.'s Tech Inc. column. And it is part of HD PowerBoost. The cute little thing about this photograph here is you see all of us gathered in front of the NAB booth in the asymmetrical sideband, and the guys on the right-hand side over here are much taller than the guys on the left-hand side, and so we have our little asymmetrical sidebands going on in the booth. Just a little inside joke here at Nautel. We're easily amused. Now, let's go forward, and this is really the special surprise. We have a special guest with us here today, Mr. John Holt. The gentleman on the right-hand side of this photograph here is WAMU in Washington's Director of Engineering. John, are you with us?
I am indeed.
Okay. It's
Thank
good to
you
hear
for
John.
inviting me.
Thank you so much for being a part of this and being a special guest on our webinar today. John, WAMU is a very special radio station, not only in HD radio circles and the fact that it's the first station ever in the world to be on with asymmetrical modulation and HD PowerBoost, but also in just simply what it accomplishes as a station. Can you toot your own horn for just a second and tell us a little bit about WAMU?
I certainly can. WMU, of course, is licensed to American University in Washington, and we're going to be 50 years old in 2011. We began our history with HD radio back in 1999 when we had an experimental operation for Lucent for the in-band on-channel system. We went on the air on Friday, May 7th of 2004 with HD radio, and the following day with a second channel. And a little later in the same, the following week, we actually had the first live broadcast on HD2 from the NPR boardroom with a pianist who was a graduate student from American University. And then in 2005, we demonstrated the extended hybrid mode with our HD3. We currently operate HD1 and 2 at 48 kilobits, HD3 at 24, all in stereo. We won the 2009 HD Radio Multicast Award for our HD2 channel, Bluegrass Country. We've given away a large number of HD radios over the last few years, and so we have a decent listener base out there. We knew we wanted to increase power and extend signal to increase building penetration and fill in the holes in our coverage within what we would consider the normal contour. And so with that in mind, we bought the NV40 car transmitter in 2009, and in May increased the power to minus 14 dBc symmetrical. And we're quite happy to participate in the demonstration of the asymmetrical sidebands, which has increased our coverage more.
John, we're looking at the COM study, technical study showing the Longley-Rice predictions of WAMU and including the adjacent stations that you protect in some cases. Can you go ahead and explain that study and what it meant insofar as your ability to go to asymmetrical power sidebands?
Well, what we have are two stations that are adjacent, WKNZ, which is currently on the air. There is actually some terrain shielding in here, and we've gone to the minus 10 level on that on the high side. This is it would be at 88.7. On the other side, we have WHMN down in Spotsylvania, Virginia. This is at 88.3. This side we have to protect, and so we're running the minus 14 on this side since we are allowed to go to minus 14. The actual study shows that we really shouldn't be, if there wasn't a ruling allowing minus 14, we should be at minus 20 on this side because of the where that station's contour falls.
Okay.
But this allows us to do the minus 10 on that side and the on the one side and the minus 14 on the other.
That begs the question about interference complaints, John. How many have you had?
None.
That's a good answer. This slide shows the process of what you'd go through if you did reach, or any station would go through if you did have complaints, and how you'd go about solving them. And we're very glad to hear that you haven't had any complaints at all. John, let me ask you, when you got the equipment to implement HD PowerBoost and asymmetricality, how hard was it to implement?
Not hard at all. This was obviously a different exciter. It plugged into our spare exciter position, which took about 20 minutes to install, and then giving Philip the ability to log in and adjust anything and everything on it. It was set up and operating, I would say, within an hour.
That's cool for the first one. Usually those things are done with a lot of clip leads. That's a wonderful thing. And your point about using the remote access capability of the transmitter is also a good point. Philip didn't fly to Washington, although I'm sure he would have been happy to. He sat in his office here and utilized the AUI from here.
That's correct.
Now let's just do that. I would like to log into your transmitter from here and show you, show everybody, I guess, the WAMU transmitter. And this is your station on the air, I believe, John.
That's correct. We see that we've got 17 kilowatts analog forward power. If we look over on the right side at the various meters, we've got 1.36 kilowatts digital forward power. We're using a 6-bay Shively antenna that's been optimized for a little broader bandwidth all the way back in 1999. That was done. So the ERP analog then is 50 kilowatts. We can also see the DCRF efficiency of 59.5%. We were under the old exciter without the power boost. We were running at 58 So because we are running the higher level on the on one side, the efficiency is down from what it would be if it was the full asymmetrical minus 14 on each side, or symmetrical rather. So, and we see the spectrum analyzer display, which I think we can enlarge here to give a better view of the
Yep, I can
of the whole
spectrum analyzer here for you.
There we go.
The interesting thing here is not only can you see that this one is running at minus 10 and this one is running at minus 14, but you notice that the mask is also altered on the display of the AUI. So it gives you a very good idea of what's going on here, and that is part of the configuration of the AUI for asymmetrical modulation. We do have a question that's come in already from our friend Louis Downey, and he says, can you address the potential for opposing asymmetrical sidebands from a main transmitter and a booster SFN transmitter to help reduce the conflict between the main HD and booster HD signals? Philip, any ideas on that one?
Sure. I think I know where you're coming from there, Louis. I think the idea would be, now it's a little bit off topic here, but it's still an interesting thing to discuss. If you were to have asymmetric sidebands for an SFN type of situation, and if you have another single frequency transmitter or booster, do the opposite. So one transmitter being low on the lower and the other one being low on the upper sideband. What that means is that the interference zones, the potential interference zones between the two transmitters would be different for the upper and the lower sideband. They would be in different geographical places. Exactly. It would be, and therefore you'd always have one very good sideband and you would never have any dropouts. So with something like that, you could set up something like a cell or a grid system of multiple transmitters, all of them alternating their sidebands. So overall, I think that is a very, very interesting idea to pursue. Mind you, the single frequency capability of IBOC is very, very good already, so I'm not sure if it's absolutely required to do that, but it's certainly an interesting concept to pursue.
Far more difficult as a process to get SFNs to work in analog mode than it is OFDM-based systems. Okay, so let's continue on, and thank you for that question. If you have questions, please do post them into the little viewer on the right-hand side of your screen, and we will do our utmost to answer them. Hopefully, somebody will ask questions easier than that last one. Notification process, how do you go about doing this? For minus 14 DVC operation, you notify the FCC within 10 days after commencing operation. There's a form online at the CDBS. For above minus 14, you have to have an informal request showing the calculation of the proposed 5010 contours on a protected station, 60-degree contour, 50-50 contour. And that's much like the chart that we showed, or the map we showed before. Note that superpower FMs must file an informal application, that is grandfathered high-power stations, for any proposed changes, and it's not guaranteed that they can raise their sidebands at all. And for asymmetrical, that's under experimental authority right now at the FCC. I will say that members of the FCC have seen the HD PowerBoost and asymmetrical in operation, and I believe they're quite positive towards adopting it when stations bring the opportunity to them. And continuing, so how much injection is enough? This is something, John, where perhaps you can help us out. How do you go about determining that you need more coverage, and what process did you go through in order to determine that WAMU would benefit from such changes?
Well, with the number of radios that we have out there, and with a number of us having radios in the car, we knew that building penetration was not particularly sufficient for what particularly in town with the a large number of people having radios in their offices. We also had some interesting spots where the extended hybrid HD3 would drop out, where the other two channels would continue. And we had some interesting spots where, just because of, even though they were in our area that should be covered, where there was terrain shielding, and we would get a dropout. So we knew we needed the increase in power. The minus 14 increase helped tremendously, and we believe that the asymmetrical has helped even more. We've had one listener who thought that it extended the coverage area about 2 miles beyond the coverage area provided by the symmetrical minus 14. We've also found that the HD3 extended signal is very consistent now, and we feel the coverage is actually extended beyond what we would might expect for some noise-free analog, depending on the terrain and so on. We can get the signal out as far as 70 miles if you've got good line of sight.
That's great, John, and particularly in the sense that you haven't gotten any complaints whatsoever with this increased power. That's in a major metropolitan area. That's a pretty big deal.
Right.
Are there any anecdotes you've gotten? I recall hearing something about various people that on their drive into work or whatever couldn't hear the station for much of the way, and now it's pretty error-free.
That's correct, and we have people who lived in some shielded areas about 25 miles out, who and we've given HD radios to all of the staff, and one woman came in and said that she could now get the signal without any problem at all. Myself, driving in that same area, you would go over a hill on I-66, and the signal would disappear for a fraction of a second. Now it stays there. Another area further out, about 35 miles out, where the signal used to disappear, that was the extent of the coverage area, is now solid for another 5 miles or so, and has 1 or 2 dropouts for another 10 miles beyond that. So we're very pleased with that coverage. But a lot of people have said that they can now get the signal. They can get it in their apartments where they couldn't get it before, or it would be intermittent, and now it's continuous, and they don't have to worry about sticking the antenna in a certain way or wetting their finger and holding on to it and to get signal. So we've got some good reports on the coverage that this has provided us.
That's excellent, John. Thank you for sharing that information. I think that's really the key for the listeners is if I go to the expense, if I go to the trouble of all these changes, am I really going to see a demonstrative difference in the coverage of my station? And your experience in a major metropolitan area is certainly a worst-case type of thing that really helps people understand what's possible, and that's wonderful. Talking about HD PowerBoost, we really kind of skirted around it. It's part of the package of asymmetrical modulation is part of the HD PowerBoost package. It's a Nautel innovation which uses peak-to-average power reduction, PAPR techniques, to the entire transmitted signal. And Philip, would you like to explain just a little bit? Don't get into the rotating vectors, but...
Yeah, I don't want to make everybody's head spin. But yes, we do want to be very careful here and differentiate. Asymmetric sidebands and PowerBoost are linked at the technology level, but they are certainly different concepts. It is HD PowerBoost that makes asymmetric sidebands happen, and that is the challenge with it. It's not just simply bumping up scale factors or anything like that on one of the sidebands, whatnot, but it's asymmetric sidebands is very, very closely tied to the peak to average power reduction technique. The two are sort of fighting with one another. If you just bump up one of the sidebands, you will lose the effects of the peak to average power reduction. However, what we have done is we've rolled the asymmetry right into the peak to average power reduction algorithm, and by doing that, we can do it efficiently. It is not that hard to bump up one of the sidebands, whatnot, using filters or anything like that. That's not really that hard to do, but you will lose your peak to average power effect, and you will need a larger transmitter. It is actually a little bit contrary. Even if you were to just drop one of the sidebands without PowerBoost, you might actually need a larger transmitter because the peaks now are starting to become bigger. It's a fairly complicated topic, but the key thing to remember is that HD PowerBoost is making that happen.
Okay, that's great. And HD PowerBoost does two things. It allows you to get more power out of a transmitter. Pardon me. And it allows you to get higher efficiency at the same time. Can you explain how you can get more power out of a transmitter and get higher efficiency at the same time?
Well, it's very analogous to audio processing. It's really the same effect. If you find ways of minimally impacting the signal and taking it out to the peaks, you can bring up the average using the same linear range, the same amplifier. And by doing so, we can push up the average power in our amplifiers without changing its operating point, per se. So we get more power out of it with the same losses. So that is the improvement in efficiency that we get out of that. Mind you, it's very hard to quantify what you can expect in terms of efficiency improvement, and we'll get into that in the next couple slides with the WAMU example, because it very much depends on your operating points. Maybe you could switch to the next slides, and I can take those. Or?
We will in just 1 second. Well, first off, we want to say that the option of HD PowerBoost is priced at $5,000 up to 10 kilowatts and $10,000 for above 10 kilowatts, and it's available in Q1 2011. I want to hit those while we're on the slide here. Those are important ones. Now, when we introduced HD PowerBoost several years ago, and we brought it to the show, what it really was a massive quad-core PC running flat out. And what we've done today is to reduce that to improvements in our existing NV exciter that will allow us to provide that functionality while changing to the new upgraded exciter.
Well, that's exactly right. The reason why we needed such a high-power industrial PC was the algorithm that we've come up with is very CPU intensive. Just for comparison's sake, one way to illustrate that is in our new exciter card, we now have about 10 times the computational performance compared to the standard Ubiquity XGen solution. It will work with the XGen solution in conjunction with that, but over top of that, we've given it about 10 times the amount of horsepower, and with that, we can get much better results.
Okay, so let's forge on here. So here are some, pardon me, some assumptions and some analysis of the savings that one might be able to expect using HD PowerBoost. And you can see the dollar savings based on a nominal value of cost per kilowatt hour of improvements in AC efficiency, AC to RF efficiency, using an NV40 24 hours a day, 7 days a year, a week, 365 days a year, over a year period. So it is possible to get a relatively quick return on investment in just the cost of reduced electrical power. And this doesn't even include, if you're in a location that may require air conditioning to cool the site, it does not include the fact that you've got a lot less cooling to do as well. Continuing on here. So let's look at what happened with WAMU. When the equipment was shipped down on the 23rd of September, but before it was installed, you can see WAMU was running minus 14 dB at 17 kilowatts, and the DC to RF efficiency was 58.3%. And then 2 days later, after the installation of this gear, and Philip had set it all up, we're still running 17 kilowatts, and it's still at 14 dBc, but now that 58% is up to 66.2%. And that's a very substantial difference in the coverage now, or in the electrical cost. Now, WAMU chose then to extend that minus 14 to minus 10 and minus 14 in that symmetricality, and even so, the efficiency was increased over what it was before PowerBoost. So it gives you an idea of the functionality that PowerBoost provides. Now, as a transmitter manufacturer, you may be wondering, what a transmitter manufacturer has to go through in order to do some of this work. One of the things is that there are two different issues which define how much a transmitter can produce in digital mode. One is the linearity, that is making sure that we don't exceed the spectral mass. And the second is thermal dissipation. When you change from class C to class AB, the amplifier becomes less efficient, and there's an increase in thermal dissipation. So one of the things we had to do, we actually had to look at we took the tops of the transistors right off, and we aimed a thermal camera at those, and we were able to then measure in operation these amplifiers and see what the actual temperature was at the silicon die inside that amplifier. And this is the thermal camera image of that same thing. So you can actually see that dual device there and the two silicon dies inside there, and the colors represent different temperatures. So then what the engineers do is they take all the headroom factors that a manufacturer will typically have in terms of maximum temperatures relative to the device manufacturer's recommendations, etc., and provide enough headroom so that we can continue to have the reliable transmitters that everybody expects. So Nautel then has developed a range of solutions for increased HD power level, for -14, -10. We've developed exclusively the HD PowerBoost, which is this improved algorithm that gives you more power out of a transmitter, but in addition, at the same time, gives you increased efficiency. We've provided the opportunity for stations like WAMU to go on the air with asymmetrical sidebands. No other manufacturer today has those two features. And this has been provided on the NV series of high-power solid-state transmitters, and it is also coming as a feature of our new low-power VS series transmitters. And this is the other little surprise that we want to share with each of you today. Philip has been kind enough to go down into the engineering lab and set up one of the VS1 transmitters that we have in the engineering lab for HD PowerBoost and HD using the VSHD device. And we actually are showing on your screen right now the VS1 transmitter operating in -10 and -14 with asymmetricality. HD PowerBoost is running on a VS transmitter. So it's not available for shipment. I can see the phones lighting up as we speak, but it is coming, and it is something that we're very proud of, that all of the FM transmitters that Nautel manufactures will be able to take advantage of this technology. Would you like to say anything about this? It's kind of early here. It's not all the bugs are out.
Yeah, exactly. So I don't want to jump the gun too much here, but certainly we're quite happy to get the power performance that we're looking for, and it seems to be working quite well.
Very good. And now, when a station is considering the possibility of going to higher power, there's a number of different criteria that will help to determine their requirements and what size of transmitter is going to be needed. And in that is the mode. Are they going to be operating in MP1 mode or MP3 mode? MP3 mode has more peak to average power requirements. The injection level that will be chosen, whether PowerBoost will be used or not, no PowerBoost. Actually, the frequency has an impact on the effectivity of power capability on a transmitter. The VSWR capability you require has an impact, and then the headroom. I mean, there's a standard philosophy within Nautel for 3 dB headroom under the mask, but in addition to that, what kind of headroom do you want to have in your transmitter? So this is a very iterative process, and I would recommend that you talk to your Nautel sales representative, and they can work through these various issues with you and determine what size transmitter may be required in your application. So in general, just as a wrap-up, the NV series is capable of all the way up to 42 kilowatts in -10 mode. That's combining two 40s together using HD PowerBoost. And we have solutions, single box solid state solutions for all of your HD radio needs going forward. And with that, I would like to thank John Holt with WAMU in Washington for being our very, very special guest. Thank you, John.
You're welcome.
And if there are, I haven't seen any more questions which have been pasted to our questions, but if there are questions, please do send them. We will answer them offline. And we thank you very much for spending 45 minutes with us today. I'm Chuck Kelly for all of us here at Nautel, thanking you for being a part of our webinar. Bye for now.